by just that's even if I mean, there must yeah, so that you can do that. There are many things that you can play around.
Yes.
Yeah. So you know, as long as you understand the story, that's
Anyway, yeah, it's all right. You can find some paper that's
yeah,
I didn't get it.
yeah.
Eleanor sounds regards.
Oh,
Very good.
thank you.
Ours are passes.
Yeah. There is usually
So good morning, welcome back to the conference. We have 4 talks today. They center around flat band systems, several packaging series, and also Ferroelectricity. And so the first speaker today is Mazin, and he's going to tell us about fluctuation-driven phenomena in Kagome-net magnets.
Okay. Thank you for inviting me here. As Prima mentioned, it's nice to be in Minnesota when it's not cold and windy. And I just recently watched this popular serial Fargo, and I left with the impression that there's always snow here, so it's 365 days a year. Anyway, I'm not going to speak about flat bands at all, and I'm actually, to be honest with you, I don't believe that they play any interesting role in this material at all.
Tell them what you read.
But all right. Anyway, I'll speak about a few other things. So the work is a truly joint work with my experimental collaborator who was snatched from us by the University of Notre Dame. And it was basically, we worked in a mode that he would come with some exciting experimental results. And then I will try all I can for starting from band structure calculations and ending or model calculations or just plain old intuition. And eventually we will figure out the picture that we both like, and we're going on with that. So I will speak about 3 different unrelated, probably manifestation of spin fluctuations phenomena. We are sort of there, often be subconscious and think that the main role that fluctuations play, particularly in metallic magnet, is basically suppressing the mean field magnetism or depressing it. It's like changing ordering temperature, for instance. But turns out that there are quite a few more interesting things about it, and the one would be about this topological Hall effect, or more correct term would be geometrical Hall effect, and then somehow they can affect the actual magnetic phase diagram due to fluctuations, and then something which we don't understand. I'm pretty sure that this is correct because we now have multiple pieces of experimental evidence that the spin fluctuations modify in a very non-trivial way the canonical anomalous Hall effect scaling, and we don't understand why. So topological Hall effect. So I will speak mostly about this material, but we know now there are examples of other materials in this family and outside of this family, and that's basically what I will briefly speak about. Something about the material. It's magnetic Hamiltonian and how it all adds up. So probably most of you know this classification of Hall effect. There is a which is very often abused, I would say, but there is this sort of mythology that ordinary Hall effect is proportional to magnetic field, and anomalous Hall effect is proportional to magnetic moment, which is absolutely not true. It's just coming from this 1930s when people were working with multi-domain materials, and then magnetization and anomalous Hall effects for completely different reasons are both proportional to domain disbalance. So this is plainly wrong, but then more correct would be that there is a that ordinary Hall effect is something related with electron charge, but not spin. Anomalous Hall effect is something which relates with spin, but not charge, and requires spin-ordered coupling. And then there is this topological Hall effect, which is a geometrical effect. It requires electron to have spin. It requires a spin to electron with a spin to follow sort of non-coplanar arrangement. And then this very beautiful work, it generates.
Question, sorry. Does this include disorder at all? Because disorder will also generate so-called anomalous Hall contributions if you have time reversal break.
No, it does not include, it's not really subject of this talk. And in fact, the proper classification of Hall effects is very non-trivial thing. It's probably not unique. There are cases which are which you really should think hard whether you want to classify them. I mean, the distinction between the first and the second, on one hand, and second and third is a little bit more clear because one is a charge effect, the other spin effect. This is sort of fuzzy thing. But in the first approximation, you can say that this is a Berry phase is sort of like accumulated without spin-orbit coupling just because of geometry. So yeah, so this is now our material. This material, which I don't show, but this material basically consists of ferromagnetic planes that happen to be Kagome, but is completely irrelevant. It's a very good metallic ferromagnetic plane of manganese, and they are interlaid. For some reason, I thought that I had a picture of. Don't I have picture of? No, I think it looks like I don't. For some reason, it disappears. But anyway, just imagine ferromagnetic planes which are sort of rotating with respect to each other, and we know why. It's not Zelshinsky model or anything. It's just pure frustration of first, second, and third exchange. And it's again, it's very well known that they form in zero field. They form this standard helical spiral. Now, when you apply magnetic field in the plane, at first the spiral starts distorting a little bit. Its hard effect susceptibility is low. At some point, you have spin slopes, standard spin slopes. So this helical spiral flops into cycloidal, canted cycloidal spiral, or also called transverse conical spiral. Then there is another transition, which is less interesting for us in this talk, into something called fan-like phase. And then forced ferromagnetic phase. So that was this phase transition were delineated in the experiment. They didn't know about this phase at all. It came out magnificently from the calculations and then turned out to be completely confirmed. Now you have again, so this is the mathematical expression of this, what is called topological Hall effect. So basically, if you have this, if this is continuous approximation, you can also write it in a discrete way. So this, we actually saw that, I think, in the last few days, a couple of times. So there is this triple product of two derivatives along two Cartesian coordinate, and then that generates topological field and so on. Now, if you have a single helical spiral, it's coplanar, so this thing is obviously zero. You can have two helical spirals, and after a little mass, you can see that they still have zero topological field. If you have three helical spiral propagating in three different directions, that's basically skyrmions. So that was also very well known. Now, the interesting thing, what if you have transverse conical spiral? You can write it in this way, where a combination of uniform magnetization and cycloidal spiral. Again, you go through this mass, you find that this magnetic field is still zero. Basically, the reason is that it only that propagates in one direction. But the funny thing is that if you add to that single helical spiral propagating in the plane, and you remember the plane is ferromagnetic, no other phase have been detected. There it says a very strong ferromagnetic coupling in the plane. So this would be, this helical spiral propagating in the plane would have to be a finite energy excitation. It would cost energy to do that. But if you add that and then again go through this math, then you can find that there is a topological field along X. So if your Z direction is the direction of your spiral perpendicular to the plane, then and it's flipped, and it's flipped in such a way that net magnetization is along X, external magnetic field, and then you add one spiral propagating along Y, then you generate this very simple topological field. Now, so Oh, somehow it, okay, I don't know, I'm sorry, some things got misplaced. I think I guess I was rearranging token at some moment, forgot to remove them. Anyway, so you can make a step back, that's okay. So this is the material, right? This is this black balls are manganese, and I can see that there are two different spacer layer. One is mixed yttrium and tin, they're ordered. And here's this one, and then there is one which is pure tin, and this is this blue thing here, and it turns out that G1 and J2 have these interactions are antiferromagnetic, and there's also J3. They're frustrated, and because of that, that's formed this spiral. Now, the full Hamiltonian, to describe that, consists of interplanar exchange, which is very strong ferromagnetic, intraplanar, which, as I say, depends, and G1, J2, they're different. Then there is a single site anisotropy, which is for this material. For manganese layer themselves, it's an easy plane anisotropy. Then there is it will turn out to be important in one particular case. There is also Ising interaction between the spins. It's allowed by symmetry. And of course, there is Zeeman interaction. So that's what there's an antiferromagnetic ordering is 340. So this is this incommensurate helical spiral, which is actually very quite close to commensurability, but not exactly. It's not exactly 0.25. This is experimental data. So if you apply magnetic field, particularly at low temperature, you can see one discrete transition and one subtle transition, and then it saturates. And this is the spin flow transition that I described into cycloidal spiral. Of course, if it's perpendicular, nothing happens. So the question that one question that experimentally posed to me was that, well, yes, we understand what that is, but what the hell is happening here in magnetic transitions? They did neutrons, and neutrons are interesting because you start with a slightly incommensurate spiral here. I think I should have numbers here, right? So you start with this 27, then it changes slightly to 0.28 at particular magnetic field, and then it changes again to now commensurate phase, and suddenly a satellite appears at 0.5, a double wave vector. Was quite intriguing, curious. So this is the phase diagram derived from the experiment. That's my role was only to put labels on these things, and that's this you already saw that. So we will again. So this is the only phase where they something that begs to be interpreted as topological Hall effect, not in any other phase.
So is there a similar signature in sigma xy or in rxy?
Yeah.
Is that
I will show that.
Oh,
yeah, I will speak about that. So yes, so there you can actually try to minimize, to simplify this moment, as Einstein said, that the model should be as simple as possible, but not simpler than that. So it turns out, depending on what you want to do, this as not simpler than that is different. Most things you can describe in this minimal model, where you only have this Heisenberg interaction between the plane, plus very strong ferromagnetic coupling inside the plane, and nothing else, and small anisotropy. But from what we can see, you can see that there is a considerable difference between intraplanar, which are also frustrated in interplanar and intraplanar. So that sort of suggests that there is some Merman-Wagner physics in the game, and Merman-Wagner physics means that there are long-range fluctuations propagating in the system, which have hard time to order, logarithmically hard time to order.
Yeah. Why are you talking about Merman-Wagner? I mean, you get the factor of 5 at best, so you get a log of 5, which is.
Well, first, it's a little bit different because these interactions are also frustrated.
Okay.
So if you sort of try to map them onto a number, that number would be smaller, maybe by a factor of 5. And yes, it's not as strongly, but what I'm trying to say is that there will be fluctuations which are sort of reminiscent of Merman-Wagner. It's a fluctuating system. It's a fluctuating system of the same sort, but it's pretty far from real Merman-Wagner, of course. And the ordering temperature is high, it's like 340 Kelvin. So of course, yeah. But if you think what you would have just from this number, you would get order of magnitude larger. All right. So this is this view. Now I'm gradually unsimplifying the model. Now I'm adding this Ising interaction, and I can tell you why. And the reason is that the pitch of the spiral is determined by the ratios of J1, J2, and J3. Particularly J1 and J2 is very important. Now, single ion anisotropy does not affect the spiral pitch. So the question why they have a couple of percentage change in the spiral wave vector was unclear until I did calculation and found that actually this term is comparable and actually twice larger than single site anisotropy is interestingly is easy axis, but Ising anisotropy is easy plane and it's about twice larger. And then what happens is that when you flop your spiral from helical to cycloidal, the Heisenberg J's don't change, K doesn't change, but in calculating of spiral pitch, what happens is that in one case you sort of add JZ, in another you subtract JZ, so you have a small change in the ratio, and this change is about 1%, semi-quantitatively consistent with the delta Q that they observed in the experiment. So that now then this I can use calculated parameters and then try to do that. It's not definitely not perfect fit, but it's qualitatively quite nice. And you have this transition here, which very reminiscent. And then the question is, what is this phase? Yeah.
And why is this transition a function of the field?
Ah,
Why is the transition as a function of the field? So far, you just explained that there are different J's.
yeah. No. The first transition is just standard spin flop. You came a few minutes later.
No, I came when you also talked
Yeah.
about.
So this is spin flop. That is a mystery so far.
Yeah.
And I will tell you what it is.
Just a question.
hmm?
So if there are strong fluctuations, would it be possible to consider higher order terms like quadratic instead of biquadratic?
That's actually a very good question. And I did not look for biquadratic coupling. Let me put it this way, like whatever, I think Laplace told to Napoleon, I didn't need this hypothesis.
Maybe
but
instead of iron.
You're absolutely right. I mean, in metal magnets, particularly biquadratic terms are very, very often non-negligible. And it's very possible. I didn't try to estimate that. But it does look like they change things qualitatively, maybe quantitatively. In fact, I more than agree. I think that there's a role of biquadratic coupling in metallic magnets is underestimated routinely. Okay, so anyway, so this is now the Hall effect. This is from a different paper published before ours, and you can see that this is Hall is very small. And then suddenly, in this particular part of phase diagram, it becomes larger. And in fact, it's hard to see here, but in fact, it actually grows with temperature. So this is the phase line that Nirmal and his collaborator drew, and that's a measurement. And you can clearly, it's very hard to disentangle anomalous Hall effect, also Hall effect, but in this case, it's quite clear that there is something else is adding in this range. So you can make this sort of poor man's subtraction, like try to interpolate between that, and then you get basically depends on how on your eye of the beholder, but you get this big peak here. So this is if you try to actually extrapolate a bit more carefully, you get peak which is about this. I mean, Nirmal that I drew by hand. Nirmal did a better job analyzing that. So now let me introduce the what we sort of new mechanism for this topological Hall effect, which I associate with nematic transition, nematic order in iron based superconductors, surprisingly. If you remember, many of you contributed to that, and you know that there you have fluctuations at two different wave vectors, and in the trigonal phase, fluctuations are have same amplitude, but when you go below nematic transition, you still don't have magnetic order, but fluctuations at one wave vector appear to be stronger than in the other, and that breaks the symmetry. something very similar happens here. Now you remember this expression that that is easily derivable, that topological field is proportional to magnetic moment and to wave vector of this added magnon and the projection onto the axis. And now you can just write with simple thermodynamics and calculate the expectation value at finite temperature. And of course, the point is that this topological field couples with external field. There's the same symmetry, there's corresponding term in the Hamiltonian and so on. So this is a pretty standard thing. And if you just do this integration, you derive this formula. There is, of course, unknown proportionality coefficients, basically coupling between external field and topological field. But otherwise, it's proportional. It's a simple function of magnetic moment as a ratio to saturation moment and temperature in its linear external field. So now that is the fit of the experimental data that Nirmal did to this formula with one parameter, and that is this fit. And he also looked at the intensity, the area of this fit as a function of temperature, and it's linear. So it's amazingly simple. And
Sorry,
I-
how are you getting something non-monotonic from this formula?
sorry.
How are you getting something non-monotonic? Is the M as function of H?
Yeah, M is function of H. Yeah.
Yes. But is it going down because you're going away from this?
Yeah.
Because Bx is going to 0?
Yes, at the saturation, that becomes 0. So now we have observation of basically the same effect in another material, the same family, and a material of completely different families. This paper will be probably posted on Quantmat in a few days. Also, magnetic spiral, completely different. So anyway, so there's a long list of experimental observations which in retrospect are very easily explained, but they were not when we started. And then this discontinuous change of scattering intensity by a factor of 2. And I skipped that, but as a matter of fact, so this is a new phase which like intersleeves between this transverse conical and forced, and that is the planar phase, so it has no topological Hall effect, and it's strictly commensurate, and it has different periodicity for the X projection of the moment and Y projection of the moment. And one periodicity is twice larger. I'm sorry, I should have put a picture here, but I didn't. So anyway, so this entire Newton phase diagram is to minute details is explained by this extremely simple model. So now the second piece is ferrimagnetism with spin orientation in terbium. So terbium is a very interesting material. You replace yttrium by terbium. Terbium has a strong magnetic moment, and it also has a strong easy axis anisotropy, which conflicts with easy plane anisotropy of manganese. So what happens is that at 0 temperature, material is basically easy axis. So this is everything is aligned, and it's aligned along Z because terbium wants to do that, and terbium is coupled, exchange coupled with manganese, and it's stronger than manganese. But then at some point, not that there, I think it's just right here will be an L transition at 450 or something, and at 300, it's an absolutely discontinuous jump in magnetic moment, completely spontaneously turn from easy plane, easy axis to easy plane like this. Just with temperature. So this sounds like, see that Colin is sort of looking unbelievably. How the hell can that be? So it's actually very simple. There is this, there is exchange, apart from our old exchange coupling J1, J2, and J3, there is also what we called J terbium, which is exchange coupling between terbium and manganese. Now, because it's actually antiferromagnetic, but it doesn't matter because if you integrate out terbium moment, you get effective ferromagnetic interaction. That will prove to be important. So basically, there is additional component, effective component adding to J2, which is ferromagnetic. And originally it was antiferromagnetic. So that's one thing, but that's not why this spin. But why this reorientation happened, that will prove interesting later. What happens is that there is a terbium doesn't really talk to each other. The interaction is very short range. Terbium only talks to the to manganese. So it's like a free Curie ion in external magnetic field, while manganese is very strongly held together by this by intraplanar interaction. And moreover, because of this very vague proximity to Norman Wagner, what it does actually, that magnetic moment of manganese, if you look at it, and this has been measured, magnetic moment of manganese actually changes very little until very close to phase transition, which is very typical for materials which are destroyed by these long-range fluctuations. So manganese moment, well, it fluctuates a little bit, maybe fluctuates a little bit more with temperature, but not that much more. While terbium, being just basically a free ion in external field, it just does 1/T, like Curie thing. So it starts fluctuating much better. So effective moment of terbium is, and it also is also experimentally measured, depends on temperature much more strongly. So at some point, terbium, and this is single site anisotropy depend on moment quadratically. So at some point, effective magnetic moment of manganese becomes too small to overpower of terbium to overpower magnetic anisotropy of manganese, and at that point, it suddenly becomes the net material anisotropy becomes easy plane, and you can write the standard mean field theory of that, and you get it. But you get this. These are you cannot go too low in the temperature, in fact, because it turned out that terbium anisotropy is not quadratic. It's another well-known phenomenon that anisotropy of F ions can have quartic and sextic terms, which it does, but at high temperature, they don't matter. So everything is very simple. Now, another manifestation of the same physics is this erbium manganese 16-6. So this is another interesting thing. Without any application of magnetic field, it starts with the with this collinear structure, very similar to basically the same as terbium. So erbium moments are vertical. It has also easy access anisotropy, blah, blah, blah. And then at some point, it suddenly switches into incommensurate spiral phase. Wow. Oh, okay. I'll try to. Anyway, so it switches into this phase with temperature, and again, for no obvious reason. It turned out again that what happens is that there is this additional interaction. This J2 is being modified by interaction mediated by erbium, but because erbium is strongly fluctuated, this interaction is very temperature dependent, and it's so conspired that at some point the J2 switches from net ferromagnetic to net antiferromagnetic, and the system switches to the spiral. So anyway, so this is a DFT calculations confirming that. There's also topological Hall effect of similar type observed here. Just very short note, because it's not subject with stock, exactly the same mechanism appears to be instrumental in this very interesting compound, but there are fluctuating manganese in the middle and then ferromagnetic planes like this, and you can tune this susceptibility of this intermediate layer by temperature and chemically by pressure and temperature, and it generates, and we fully understand that quantitatively with phase diagram, amazing things like re-entrant antiferromagnetic behavior at some point, at some concentration, it's ferromagnetic at higher temperature, and so it can switch. That all comes from this fact that interesting and non-trivial dependence on magnetic susceptibility of this intermediate layer, which you integrate out eventually. So now finally, fluctuation anomalous Hall effect. So this is again back to this terbium manganese 16-6. It has not topological, but large anomalous Hall effect because it's ferromagnetic to be precise, and you can measure it. That was measured. So this is measurement of Nirmal and other. They are extremely similar to the measurement of Princeton group, which made quite a splash. But this is another interesting moment. So there was, I will show next slide. Oh, actually, it's here. There is a, not really mythology, it's actually a good model for some particular assumptions, which said that your anomalous Hall conductivity should scale in some particular way with longitudinal conductivity. And they wanted to prove that, but it turns out in this case it does not. But they didn't like to show that, so they plotted that on double logarithmic scale. And the funny thing is that them being Princeton people, they didn't even realize that linear on the double logarithmic scale is not linear in the normal scale. So that was just amazing. I mean, but anyway, when you do that right, it turns out that this standard scaling does not describe the data. But if you add additional term like this, then it fits the data to a T really well. And the origin of this new term was not clear at all, but one is known as side scattering and side jump. It's known also as a nice theory showing that phonons actually canceled out and don't contribute, but that theory does not apply to spin fluctuations. Again, I don't know, somebody smarter than us can maybe do this full theory along the line of Crépio and Bruno. But the fact is that the existing theory does not apply to spin fluctuations, and empirically they just introduce this additional simple term, and it works not only for this material.
Oh, Igor, could I stop you for a second? Concerning the skew and I guess
Side jump.
and
Yeah.
side jump scattering, they contribute also like sigma xx square. They could also in principle give you a term which is linear in sigma xx to the power 0. So they also contribute to what
You're absolutely right. They
and
work.
also can be 1 over sigma xx. It depends on how far you go.
No, I don't think. Okay, I thought I didn't see any variant of the model which would generate this
And
term.
it's
But there are
very
some other
careful
terms. You're right, and
calculation.
there are, and in principle, they shouldn't scale specifically with sigma. Long there, you have to distinguish between residuals. So there are many different. But for some reason, the experimentalists really religiously apply this simple formula all the time. But anyway, and it works in many cases, but in this case, it did work for some other materials, the same family, but not in, but in this one, just adding this one term makes really perfect fit in all cases that we discovered so far. Moreover, even more interesting, if you compare these two materials, these materials are both have the same magnetic structure for completely different reasons, but one of them has very strongly fluctuating spin, which is terbium, and the other has much less fluctuating manganese, but also have a lot of impurity scattering because it has gallium here. So you would expect that the term which is controlled by impurity would be much smaller in this case, but the term which is controlled by fluctuation, which we believe is due to fluctuations, would be much larger, and that's exactly what happened. They scale oppositely. I think I'm basically finished. So that is So that's it. So this is a summary. As I say, we don't have any microscopic theory, but we have several. There's also another example with another material. So we have at least 3 different examples that this scaling works perfectly well, and also agrees with the intuition that you may have from how much fluctuation you have in the system, how much impurity scattering. So right, okay, I'll stop here.
Questions?
Yes.
Yes, Igor, as a follow-up to Daniel's earlier question, how robust is the topological Hall effect to disorder? Is it more sensitive to disorder than its cousins?
From what I know from experimentalists and also my sort of intuitive understanding of the physics, it's not very sensitive.
Really? Okay.
I don't think so. They can see that in different samples, and I don't really see why it should be, because the only thing you need to have some sort of like loop orbits where the spin is doing this thing, and that shouldn't be that much affected by impurity. I don't think so.
But I think just to comment on that, in the measurement, when you measure, for example, the anomalous Hall effect, you cannot really distinguish whether the contribution comes from disorder or from the intrinsic one.
Absolutely, yeah. It's a big challenge, and it's routinely swept under the rug.
Exactly.
It's
As
a
you
big-
probably know, and sometimes the
It's a
sort
very
of contribution
it's a very big
overwhelms
problem.
changes.
And I kept telling my collaborators, don't try to do any fancy theory. Just if you see by your naked eye that there's a bump here, then just try to smoothly extrapolate from the neighboring region and call the residual topological Hall effect. There's no real theory about how to tell them apart.
Very quickly, returning back to the issue of the pitch of a spiral. When you showed the data first, you said experimentalists wanted you to look into something which resembles flattening of magnetization at some intermediate fields. There was some story. And then you said that there is a variation of a pitch of a spiral from point 27 to 29 and then to 25. How much of this is just a noise and how much is what you can explain?
There is no noise. It's the data are fantastic. I mean, this is from Rebecca Daly. There was a follow-up paper. when she-
How much it's in the theory? Because
Completely.
you explained that there is
Well,
no
yeah, well,
connection.
okay. Everything that I showed fits to the theory like to a T. Everything is explained to minute details, but there are some other things which we cannot explain. And specifically, there is a double spiral. They actually see a second spiral with a different pitch, which is temperature dependent, and they sort of there's temperature dependent change of the pitch. That I didn't show, and that I cannot explain.
That's why you didn't show it.
Yeah. I would have it for just entire talk about the spirals, but I didn't have time for that. That's a challenge.
Yeah, for the terbium compounds, you have, pretty high nail temperature. I didn't see it, so I apologize if I missed it. What is the role of crystal fields, if anything, in your calculations?
Oh, this crystal field is everything. We did calculate the terbium anisotropy very well, and I mean it's a whole different, very very beautiful story. How the thing, the story is that normally you expect magnetic anisotropy to be quadratic. It's not the case here, and that's specifically because the crystal field here is a perturbation on top of spin orbit coupling, not other ways around as in D material. And you can actually write this, you can calculate for, and DFT completely messes up that because it doesn't, it has self-interaction with F shell and it doesn't work. But you can do calculation of crystal field parameters using a full shell, I think it will be gadolinium. And then you can use it as an analytical theory, which involves Wigner coefficient and some simple but long formula, and then it works very, very well, and it's very non-quadratic. Anything else? No?
Next, we're going to hear about the ferroelectricity, geometrically, magnetically driven ferroelectricity in perovskite crystals. By Xianghan.
Yeah.
Right.
Right. First, I would like to thank the organizer for having me here. I'm very glad to present my research about geometrically and magnetically driven ferroelectricity in perovskite crystals. So here's my acknowledgement. So most of the sample synthesize and microscopy were done at my PhD advisor, Professor Song Chong's group at Rutgers University, with the help of my colleague Fei and Kai, and the single crystal X-ray diffraction and the structural refinement. They were done at Professor Bob Kava's lab, my postdoc lab at the university, at Princeton University, and my collaborator Jan Musfield and Kevin Smith at Tennessee University. They did the optical measurement. And Beth Nordic at UC Merced, she performed the DFT calculation. So here's my outline. So in this talk, I will introduce 3 different systems. They are strontium tin oxide, lithium strontium niobium oxide, and samarium medium oxide. So we just recently got very interesting data on the samarium medium oxide. So all of those compounds, they have a perovskite related structure. And all the experimental data I'm going to present are on single crystal. So our keyword in this talk is ferroelectricity. Ferroelectric material hosts spontaneous polarization and is switchable by external electric field. And this ferroelectricity was firstly discovered by Joseph Velasek. He was a professor here at the University of Minnesota. And when he was a graduate student, he found this switchable electric polarization in this hysteresis loop of a Rochelle salt. So the Rochelle salt is the first ferroelectric material that ever been discovered. And now, after like more than 100 years now, so the ferroelectric material is still having tons of applications in our technologies. For example, we can use the spontaneous polarization as a media to store information. And also due to the field tunable nature, we can use ferroelectric material to make sensors and actuators. And moreover, you must be familiar with the phase diagram of a doped strontium titanium oxide. At low temperature, the ferroelectricity have something to do with the unconventional superconductivity in this material. So overall, ferroelectricity is still a very popular topic that is closely related to frontier research directions in quantum matter physics.
I think there's a laser pointer. Do you want to use that?
Oh, was it
Right of your computer?
this one? Oh, good. Thank you. All right, so one of the simplest example for a ferroelectric material is AbO3 perovskite. You know, at high temperature, the crystal structure is ideal cubic without any distortion. But if you cool it down below the ferroelectric transition temperature, there will be a ferroelectric polarization induced by the off-center displacement of the B-side atom. And so in this type of ferroelectricity, the driven force is directly the lattice instability. So it is called a proper ferroelectricity. And unfortunately, the proper electricity in AbO3, they are not common. There are only very few material examples, such as doped STO, BTO, and PCT. Instead, a much common type of structural distortion in AbO3 is rotation and tilting. So what does that mean? Rotation and tilting means there's no relative displacement of a B-side atom. Instead, the entire octahedron is having this rotation and tilting mode. And this kind of distortion will distort the lattice from cubic to orthorhombic. And the space group of the orthorhombic lattice is PNMA. So if you look at the database, actually the fact is more than 50% of the reported AbO3 material adopts this PNMA distorted orthorhombic lattice. But unfortunately, this orthorhombic lattice is a central symmetry. It does not host the ferroelectricity. So one question for us is if we can take advantage of this commonly existing rotation and tilting mode to create a ferroelectricity. So if we can find this mechanism, that will lead to discovery of tons of new ferroelectric material in the perovskite family. All right, so first let's look closer into why the rotation and tilting, they don't give a polarization in AbO3 perovskite. So now we have this image of the AB plane of a perovskite unit cell. So the rotation mode does not create any polarization. And the tilting mode, it creates a pair of electric polarization, but they are opposite and equal in magnitude, so it cancels out. Even if we combine them, like we have both rotation and tilting mode, the final lattice will still have a polarization anti-parallel to each other. So it is antipolar instead of ferroelectric. And then in 2011, theorists, they come up with a very interesting mechanism. It's called a hybrid improper ferroelectricity. So the idea is instead of applying this rotation and tilting on AbO3 cubic perovskite, we have them on a layered perovskite. Then it does lead to a ferroelectricity. So the RP phase is one of the most famous example for layered perovskite. So basically the structure of IP phase can be regarded as a stacking of the structure unit of several perovskite layers, and they're shifted and there's a gap in between the different perovskite structure units. So the general formula for RP phase is A n plus 1, B n O 3n plus 1. And when n is equal to 2, we have this A3 B2 O7 structure. It's also called bilayer perovskite. So now if we have rotation and tilting on this A3 B2 O7 lattice, it does produce a ferroelectricity because here you can see the top and bottom layer of the A side atom is having polarization to the right, but the middle layer of the A side atom is having a polarization to the left. So 2 to 1, they don't cancel out anymore. And that is how the hybrid improper ferroelectricity mechanism works. And the free energy of hybrid improper ferroelectricity can be written as a trilinear coupling of the polarization, rotation mode, and tilting mode. So let me emphasize the beauty of this mechanism is although the rotation and tilting mode themselves are not polar, but if we combine them and apply them onto a certain lattice symmetry, it does give a ferroelectricity. So hybrid improper ferroelectricity is also an example of so-called geometric ferroelectricity. So after like 4 years after this mechanism has been come up with, the first experimental demonstration was done at Xianghan's group in 2015. So they made a crystal for calcium, strontium, titanium oxide 327. It is ferroelectric at room temperature as demonstrated by the hysteresis loop. And they also see the autonomic training domains. They are actually 90-degree ferroelectric domains. They have polarization 90 degrees to each other. And this mechanism not only work for bulk crystal of oxide, they also exist in thin film samples such as artificial superlattice and molecular perovskite, as well as highlight perovskite. And interesting physics such as domain engineering and negative thermal expansion have been demonstrating those systems. So it's a very popular system, but despite those progress, there's an issue related to the hybrid improper ferroelectric material, which is they tend to have large switching barrier. So if you look at this figure, you can see the coercive electric field of reported hybrid improper ferroelectric material are generally higher than the proper ferroelectric materials that we have been using. So the coercive electric field means the minimum electric field that is needed to flip the polarization. So larger coercive electric field means it costs more to manipulate the polarization, which is not good. So one question for me is, can I come up with the new hybrid improper ferroelectric material with a reduced coercive field, at least comparable to the proper ferroelectric materials that we have been using? So this is a qualitative analysis. You know, tolerance factor is a very powerful empirical rule when we deal with perovskite system. It is defined by the radius of A side atom plus the radius of oxygen divided by the square root 2 times the radius of B side atom plus oxygen. So if the tolerance factor is equal to 1, that means the size of A side atom and B side atom, they match perfectly in the perovskite lattice, and there is no distortion. But if the tolerance factor becomes smaller than 1, a distortion will be favored. So the idea is we want to find a material is a tolerance factor slightly smaller than 1, but not too small. So then the amplitude of the distortion is minimized, which means we can have a small switching barrier. So from this table, the calcium magnet oxide 327 has largest has the tolerance factor closest to 1. However, this material is not a good candidate because it is relatively conducting. So the room temperature conductivity is resistivity is 100 ohm centimeter, which means the material is leaky. The voltage cannot be efficiently applied. Then the next candidate, strontium tin oxide, becomes the most promising candidate. And the growth of this material is tricky. There are two difficulties. So first, the strontium tin oxide 327 has a relatively high melting point. It's above 2000 degrees C. And also one of the raw material, tin oxide, it vaporizes severely. So yeah, it vaporizes severely during heating. So in order to overcome those difficulties, I use this laser floating zone technique. So in this setup, basically 5 high power lasers are shooting at the sample. It can create a very high temperature molten zone. It is high enough to melt the sample. And also in order to suppress the evaporation loss, I apply a 9 pressure oxygen pressure because 9 bar oxygen pressure, because based on the phase diagram, you can see the oxygen deficient phase, they tend to have even higher vapor pressure. So that's why applying oxygen pressure can reduce the evaporation loss. So this video records the growth process. You can see this white smoke. They're actually the evaporation loss of the tin oxide. And this growth only takes like several hours, but it takes 2 days to clean up the furnace. And eventually, I'm able to get this large crystal. And
Do you have a cold finger in there or something to catch the evaporated material?
cold finger.
Yeah, you can put a water cooled cold finger in. That's the way you grow high temperature high melting point ruthenate.
Right. So sometimes one thing we can do is we can add some solvent in the molten zone to lower the melting point a little bit. But it doesn't work for this system because based on the phase diagram, it congruently melt. So what you should do is just melt it and slowly cool down, it will crystallize.
So how do you prevent the evaporated material clouding up the tube and preventing you from getting the laser power in?
Oh yeah, that's a good point. So outside the growth, we use a quartz tube. So sometimes the material can get attached on the quartz tube, but it suddenly get vaporized again by the laser slot. So usually it covers other part of the quartz tube, but not the part where the laser passes through. Okay. Yeah, so the quality of this crystal looks good. So here we have the optical microscope image of a cleaved AB plane. And the interesting thing is if we apply if we use a linearly polarized light to do the optical microscope observation, we can see the striped domains. They are orthorhombic twinning domains, and they are also 90-degree ferroelectric domains. So they have electric polarization 90 degrees to each other. And this material turns out to be really ferroelectric, demonstrated by this hysteresis loop at room temperature. And remarkably, the coercive electric field we obtained from this hysteresis loop is only 39 kilowatt per centimeter. So it is the lowest value ever reported in all discovered hybrid improper ferroelectric materials, and is much closer to the coercivity of other proper ferroelectric materials. And this low switching barrier not only work when we try to flip the domain using electric field, it also leads to a very sensitive tuned domain switching under strain. So as you can see from this video, we are like pressing the crystal, applying a uniaxial stress. It can cause a dramatic change of the domain pattern. And the unit of strain here is 1/1000. So you can see the maximum strain that is needed to reach, the minimum strain that is needed to reach the single domain state is less than 1%. So it is highly tunable by external strain. And this,
What's the time scale in this video?
oh, I speed it up by like 5 times. So
Just 5.
yeah, just 5 times. And this observation also tells us it is not only a ferroelectric material, but also a ferroelastic material. So now let's think about why we can have this A domain, B domain, this domain contrast in optical microscope. That is because it has an orthorhombic lattice. The A-axis is different with the B-axis. They are not equivalent. So this contrast in optical microscope, they're actually coming from a birefringence, right? However, birefringence does not distinguish the plus A and minus A. So that means within each orthorhombic twin domains, there might be 180-degree ferroelectric domains. They're just not visible by an optical microscope. So in order to see that, we use this piezoelectric force microscopy. So the principle of this technique is we scan the sample surface using a metallic tip, and it can map out the topography. And meanwhile, we apply an AC voltage on the sample through the conducting tip. So if there's a polarization in the sample will oscillate with the same frequency as applied electric voltage. And the direction of that polarization will be reflected by the phase difference between the applied AC voltage and the sample oscillation. So using this PFM technique, we can map out the completed domain pattern in this sample. And indeed, you can see inside each twinning domain, there are also 180-degree ferroelectric domain. And an interesting thing about this domain configuration is there are abundant charged domain walls. So charged domain wall means if you have a domain wall like this and the polarization head-to-head across the domain wall, then at the domain wall, there must be some bound charge based on the Gaussian theorem. So we can map out the distribution of bound charge based on this domain configuration. And the red color are positive charge, green color are negative charge. So let me remind you, this kind of abundant charged domain wall is not usual in ferroelectric materials because usually this charged domain wall, they combine with the much enhanced electrostatic energy. So this is something we don't understand why there are so many charged domain wall here. And in order to understand the low switching barrier, our collaborator performed a DFT calculation. So, as you remember, this free energy of hybrid improper ferroelectricity is a trilinear coupling of the polarization, rotation mode, and tilting mode. So which means if we want to flip the polarization, we can either reverse the tilting mode or we reverse the rotation mode. However, this this calculation result shows that this individual reversing of the tilting mode and rotation mode, they are not energy favorable they're not energy favorable paths. Instead, antipolar switching, as shown by this black curve, it has the lowest switching barrier, and it's likely what is happening in this system. So now let me explain what is the antipolar switching. So basically, in order to have a ferroelectric phase in 3 to 7, the rotation mode has to be in phase. In phase means we look at the column of the octahedron along c-axis. So the rotation of those octahedron has to be a same direction. Let's say both counterclockwise or both clockwise. And if we now change this rotation mode from in phase to out of phase, which means we have alternately counterclockwise, clockwise, counterclockwise, clockwise rotation, then the final structure will become a PNMA antipolar structure. So the calculation result here tells us the antipolar phase is actually the intermediate phase during the polarization switching in this sample. So basically that means we have the antipolar phase as a domain wall in between the two opposite polarization. And the switching of the polarization is done by the translation of this antipolar domain wall. And Turan also did beautiful calculation on this system. So basically, if we apply a 2% tensile strain implant, it can enhance the tilting mode, but reduce the rotation mode. And with this 2% tensile implant strain, the switching barrier of this system can be further reduced. And this calculation result is consistent with my previous arguments that the rotation mode is the most critical factor that determines the switching barrier in the hybrid improper ferroelectric system. All right, so that's the story about strontium tin oxide. And as you can see, the 3 to 7 layer perovskite, it shows a rich lattice freedom and highly tunable. And then I'm going to show you that we can even further tailor the structure and bring up more functionalities. So in this lithium strontium niobium oxide, now we have two different kind of A-site elements, lithium and strontium. And due to the different size of lithium and strontium, they tend to order in this structure. And the beauty of this structure is, as you can see, the lithium ion, they form a 2D plane, That means in this crystal, it's very likely a good host for a high mobility lithium migration. It's like a lithium not superconductor. It's a good conductor of lithium ion. So in order to investigate this possible functionality, I made a single crystal and I applied 2 electrodes on both sides of the crystal. And then I charge 200 watt DC voltage on the sample. As you can see, after 2 minutes, there's some intensity start to accumulate at the positive electrode. And if I just charge it for a longer time, like 4 minutes and 6 minutes, you see this intensity get enhanced. And then I remove the voltage. You see in 2 minutes, the intensity disappears. And if I reverse the 200 voltage, reverse the direction of the 200 voltage, the intensity just show up at the other side of the electrode. That means inside the sample, there's something lithium or lithium vacancy, they are flowing. They can be driven by applying DC electric field.
What is the intensity?
So, this is a optical microscope observation using polarized light. So we expect there's some change of the refraction index near the electrode due to the movement of the lithium vacancies. All right, and this lithium migration also bring up a dramatic change in the electric property. So first, you can see the IV curve is highly nonlinear. And if we use a slower sweeping rate, it gives a much enhanced DC conductivity. And the sample is transparent, is a semiconductor, and the DC conductivity of the pristine crystal is only 10⁻⁶ S per meter. And interesting thing is, if I apply DC voltage, 10 volts, for a while, you can see the DC conductivity is enhanced by a 3 order of magnitude. And then I retrieve the DC voltage, the DC conductivity start to decrease. All those measurements are at room temperature. The DC conductivity start to decrease, and it go back to the initial state after several minutes. So let me remind you, the carrier here is still electrons. So what is happening is the lithium migration at the electrode, it actually reduced the height of the Schottky barrier at the electrode. So that changed the DC conductivity. And so you can see at room temperature, the enhance of DC conductivity also always combined with the relaxation process, which means if we remove the voltage, the lithium ion will slowly get back to its original position. But in order to suppress this backfilling process of the lithium ion, the one thing we can do is we can do an electric field cooling. You know, the lithium migration will be frozen at a low temperature. So what I do is I cool down the sample from room temperature to 200 Kelvin, but with the presence of electric field. So this is the electric field cooling. So if I use a plus 10 volts electric field cooling, you see the diode state is stabilized at 200 Kelvin, and the conducting direction is the same as a polling electric field, and it does not show detectable decay even after 30 minutes. And also this diode state can be reversed by opposite direction of the electric field during cooling. That is because the lithium migration is frozen at low temperature, and this biased state can be maintained. So yeah, this actually there are also tons of structure transitions and different dielectric behaviors in this sample. For example, at low temperature, it is ferroelectric out of plane and anti-ferroelectric in plane. But I'm not going too much detail about this complicated structure. This diagram, I just want to give you a flavor that it's 3 to 7 as well as modified 3 to 7 layer perovskite really has a rich lattice freedom and a highly tunable and a good candidate for multifunctional applications. All right, so now let's recapture our initial research motivation. Like we have this tons of PNMA perovskite, and they are 5 minutes? 10 minutes, okay, yeah. They have in this family, they have tons of PNMA orthorhombic perovskite. They are not ferroelectric. And in order to make them ferroelectric, the one strategy is we make the lattice from cubic perovskite to bilayer perovskite. That is a hybrid improper ferroelectricity I have introduced. But if there's a possibility, like we don't change the structure here. We don't change the structure here. We find some way to induce ferroelectricity in the PNMA perovskite. It sounds impossible because the space group is central symmetric, but that's not the case if we use a magnetic freedom. So after the magnetic freedom comes in, we can still make the PNMA perovskite ferroelectric. Usually magnetism and electricity, they have a distinct microscopic origin, so we don't expect they couple to each other efficiently. But in a unique type of magnetoelectric material, the magnetization can couple to the electric polarization, which means you can induce a magnetization in a material by applying electric field. And you can induce a polarization in the material by applying magnetic field. So usually we use this ME tensor to describe the magnetoelectric response of a material.
So don't you need to bring inversion symmetry for this to be non-zero?
Yeah, good point. So to be magnetoelectric, the spatial inverse symmetry needs to be broken by the magnetic structure, not the lattice structure. Right. Yeah. And the example of this is a magnetoelectric tensor. We have diagonal term and off diagonal term. Diagonal term means the induced polarization is parallel to the applied magnetic field. Off diagonal term means the induced polarization is perpendicular to the applied magnetic field. So the example for diagonal response is a chromium oxide, right? And the example for off diagonal magnetoelectric response is a magnetotoroidal moment. So which means we have a head to tail vertex like arrangement in the magnetic structure of that material. If you have this magnetotoroidal moment, we apply a in-plane magnetic field, we'll have a in-plane polarization 90 degrees to the magnetic field. So the system I'm going to discuss belongs to this rare earth indium oxide 113 system. So I think the most famous crystal in this system is terbium indium oxide. You know, it has a hexagonal structure, and the terbium ion is located at a triangle lattice. So it's a candidate for spin liquid, and some work has been done. But that is not the focus for my talk today. So today I'm going to focus on the samarium indium oxide. So samarium indium oxide, you see, it locates at the boundary between two phases, hexagonal phase and orthorhombic phase. And the magnetism of that compound has not been reported before. The crystal has never been grown. So that's a motivation. And I start to investigate the samarium indium oxide. This is again the single crystal grown by the laser floating zone techniques. As grown crystal, a little bit dark, but it becomes much more transparent after annealing in oxygen flow at 800 degrees C. So it's a good insulator. We are able to determine the lattice structure using a single crystal X-ray diffraction. And the structure can be, this diffraction pattern can be well fitted using a PNMA orthorhombic space group without any ambiguity. And here's a schematic of the lattice structure. You see, due to the orthorhombic distortion, the A and C axis, they have similar length, but the B axis, it is a longest axis. And the magnetic sublattice of this material is a square lattice of a samarium 3+ ion. Here is a magnetism. So first, there's a clear anti-ferromagnetic transition at around 2.7 Kelvin, indicated by the peak in the susceptibility. And we also measure the magnetization as a function of magnetic field at 1.8 Kelvin. You can say the magnetization of the B axis is different with the behavior of A and C axis. There's the upturning, which is an indication of a metamagnetic transition. Okay, yeah. And in order to track the metamagnetic transition, we elevate the temperature a little bit, and we can see the kink, which is a metamagnetic transition. And here's a, so the inverse susceptibility is not linear. That means there's an evolution of crystal electric field levels in the system. And I try to fit the curve-wise behavior at a low temperature along the B-axis, and it gives effective moment around 0.64, which is close to the theoretical magnetic moment for samarium 3+. And here is a Higgs capacity thermodynamics measurement. So there's a clear peak at the antiferromagnetic transition temperature. So it's likely a 3D magnetic ordering. And the formal contribution can be fitted using a Debye equation as shown by this light blue curve. After subtraction, we get this magnetic contribution. And if we integrate the entropy, it gives R ln 2, which means the ground state for samarium 3+ here is a effective doublet. You know, samarium 3+ has odd number of electrons, so it's not surprising that the ground state has a doublet. But we can see this R ln 2, which means the energy difference between the ground state and the first excited crystal electric field level is large. That's not surprising because I found a similar compound, samarium-based oxide, 227 pyrochlor. So they did neutron, inelastic neutron, and they found the ground state and the first excited CEF level has an energy difference around 16 MeV. So anyway, the samarium here has an effective doublet ground state. And this magnetic ordering does combine with ferroelectricity. So first, you can see at the magnetic transition temperature, there's an anomaly at the, there's an anomaly, and a higher field can enhance that anomaly. And also we have a clear peak in the pyroelectric current data. And integration of that current peak gives a development polarization below the magnetic transition temperature. So this measurement is for diagonal response, which means we are collecting polarization parallel to the magnetic field. And this sample also shows off-diagonal magnetoelectric response. You can see in the off-diagonal situation, the anomaly in the dielectric permittivity is much enhanced. And we also get a higher polarization value from this pyroelectric measurement. So that means the magnetoelectricity in this system is dominated by off-diagonal response. And here is a magnetic phase diagram summarizing all the data we have. So our next plan is I'm sending the sample to Oak Ridge Lab to do a neutron diffraction to determine the magnetic structure. After having the magnetic symmetry, it may explain the origin of the observed magnetoelectricity. And also I want to convince you that this system is a also interesting system to be studied by inelastic neutron for two reasons. First, as you can see at the purple region in the phase diagram, it corresponds to a field-induced disorder state. So although square lattice is not a typical lattice for magnetic frustration, but still is a good system to study the J1, J2 physics in square lattice. Oh, sorry. And the second reason is this sample has a significant off-diagonal magnetoelectric response. So when you have a polarization and a magnetization perpendicular to each other, the spin wave along the third direction is allowed to have a non-reciprocal feature allowed by symmetry, which means the spin wave might be asymmetric under the plus K and minus K transformation. Right, that's the end of my presentation. And I would like to thank my co-authors again. So.
A couple of questions.
Mhm.
I have one question, which is in hybrid ferroelectric compounds based on geometry. Has there been studies of the phonon excitation spectrum associated with twisting and tilting in principle? Whether this be from soft mode or to the flow?
Oh, yeah, that's a good point. So I have a phase diagram of that compound. Here, you can see there's a structure transition at around 400 Kelvin or 2 bar pressure. So we do expect there's a softening of phonon at that temperature. But experiment hasn't been done before, so probably even neutron scattering can tell this phonon dispersion in this material.
For samarium oxide, you made a point about talking about oxygen annealing. That's presumably filling oxygen vacancies from
Yes.
as-grown crystals. Do you find any, have you measured sort of the as-grown samples and how do they magnetically compare to?
Oh, right. I didn't measure as grown some. I just assumed the anneal sample has better quality. I don't measure them. All the data are on the anneal sample.
So in these hybrid improper ferroelectrics,
Mhm.
has the so they have very large coercive fields, so they are not great for applications yet, I guess. But are there nevertheless any measurements of things like loss tangent, etc., to see like if one day they will be good enough for like filters and other microwave or RF applications?
Oh, I didn't think about that possibility, but I think compared to the proper ferroelectric material, the beauty of hybrid improper ferroelectric material is they have this abundance of domain, behavior, and microscopic physics. That's the thing that proper ferroelectric material don't have.
Yeah, definitely.
The applications for this lithium transport situation, can you use that as electrodes and batteries, or is it?
Yeah, for sure. It's a good electrolyte material for lithium batteries. And also this memoristor behavior can be used for neuromorphic computing. Too fancy.
Okay, then no further questions. That's thank you very much. We'll assemble it at 2040.
Yeah, I think that's reasonable. That's good.
No.
Thanks.
So I'm reminded of this calcium.
I remember a paper of actually mapping.
Yeah.
I'm gonna write this for myself.
What's the current
I have a number of follow-ups.
that material right now. Yeah. How did you, that geometry, what was actually? Absolutely, well, you just sort of put it in a, let's see, put it in a wall along the right direction, so it's like most efficiently tuned by a vertical. We should say this 45 degrees.
So,
So you want to find a straight.
yes.
We showed Toronto's calculation.
Well, I had the
use of transfer calculation here. Put a sample on the other side and by a big and measure the electric speed.
You can see that there is
就各个组织对吧？就赵林过去讲，然后就是说周老师组织讲，然后大家各个手段给你也抄到之类的。
要米还是什么来？我忘了。
当然那个赵军自己讲的，赵军做的是430嘛，不是327，所以
330也是抄的。张美山我们做很多事情是为什么这样？因为没加压呢。
没加压，但是这个事情就很难说的了。
能测3个样本，这个一个样最好。
对，所以就刚才说，就王猛他们说是大家觉得那肯定是养了dependency了，所以就退火反而更不少。
本来涨的时候高压，退火也来高压。
但是大家退火也少，所以也不知道怎么回事。但实际上越退越不高。
三方面目前是样本。
说王猛都没有样品了，王猛就长了那一根样品分给了所有人，然后别人再问他要没了，然后他也长不出来，不能复现，不知道当时是什么，就是一开始想是养了dependency了，后来发现养了dependency不是，那就要再考虑那当时是怎么长出来的，就是数据没造假，样品没造假，那到底是什么东西？所以呢，孙明老师说那个
对，
对，然后那个陈金光就说他加了那个 PR 之后，把金格 distort 了一下，然后说这个相关的。
Can you say that it's not see this slide?
I don't think so. 好像跟王猛测到的数据是类似的，所以我还不知道是什么原因的。拿出来写这样。我找了，所以找了，所以就叫 box 的 functions。
Right, thanks.
Yeah, we've been pretty.
Okay, so very although if you have posters on, please remember to take them down, once everything's over. Okay, good. So, all right. Right, so we have now two talks. The first presentation, tale of two flat bands.
Thank you, Colin. So after hearing, I want to thank the organizers first for giving me this opportunity to be here. And after hearing talks in this workshop, I decided to change my topic a little bit and change my title as well, which I definitely is only appropriate in the Twin Cities. So actually, I would like to tell you about some of our unpublished work. So our group is mainly a photo emission group, and we've been studying in bulk material systems that host topological flat bands. And I'm gonna try to give you some overview of some of the stuff we worked on at the beginning, and then for the second half, talk about some of the unpublished data on a system that hosts two types of flat bands. So here we go. So flat bands, we all know in flat bands that flat electronic bands can be induced in bulk materials, basically comparing two energy scales. One is the Coulomb interaction and one is the bandwidth. And as long as the Coulomb interaction is much larger, compared to the bandwidth, then we're in the regime where the bands have very narrow bandwidth. And obviously there are two ways to achieve this, and these are the two extreme limits out of this paper. You can crank up the equilibrium interaction U, and in that limit, we're very, very familiar with this side of the things. Here, we would see atomically localized wave functions on atomic sites and with very little overlap. And this is the case that we're familiar with in the case of Mott insulators or heavy fermions and so on and so forth. You can also obviously achieve flat bands by squeezing down the bandwidth. And in the recent years, there's been a boom of activities on this side of the world where one can realize this kind of situation where the block wave functions are not on atomic sites and they're extended. There is overlap, and but here the hopping is really quenched by the destructive interference due to the geometric frustration of the lattice, right? So as you can see, these two types of flat bands are fundamentally distinct objects, even though they both give you flat electronic bands. So therefore, they must also have very different spectral properties. And so one may ask, how do these bands contribute to or affect electronic orders in quantum materials? So this is something we want to aim to understand. Before I get there, I just want to first show you some examples, well-known examples on this side and also that side so that we get a sense of what to expect. So first, let's look at the case of large U, and this can be very well understood or represented by heavy fermion systems. And here we know that we have these heavy F electron states which are atomically localized, and they also can interact with conduction electrons or SPD electrons. And you can realize the two situations where there is no interaction between them and you end up with a small Fermi surface. And then in the other case where there is finite interaction. And this is only the situation where you can actually see spectral weight from the flat band in this situation via the interaction. So where you can see the Fermi surface. Maybe perhaps a milder version of this is what I'm familiar with more, which is the iron-based superconductors. And so here in the multi-d orbital system, we've seen from full emission and also other work that you can realize a situation where while you have different orbitals bands, their bandwidth can vary differently as you tune some tuning up. In this case, what I'm showing you here are these band dispersion measurements of energy versus momentum, and then measured as you vary the amount of tellurium versus selenium in this iron tricotinite superconductor. So from one end to the other, I hope you can see that the curvature or the bandwidth of this blue band, XY band, changes more dramatically as you go across than, say, some of the other bands, right? So this is a situation where we observe this very strong orbital selective correlation effects. That's very well captured by this slave state calculation by my colleague Chimielski's group. So on the left-hand side, this is the calculate band dispersion, and you can already see this extremely flat XY band, which is hugging the Fermi level, and it still has finite interaction or hybridization with the dispersive states. This is already in the strongly correlated metallic state, and then you go to the limit of where the XY orbital becomes completely not localized, then it's completely flat, but it loses all spectral weight, and then the hybridization is also turned off, right? So this is the situation where you have this orbital selective Mott phase. And so the consequence is obviously there will be a change in the Fermi surface topology. This is the case where you have all of these metallic states, quasi-particle spectral weight near the Fermi level, and this is a situation where the spectral weight from the XY dies, and that's seen experimentally in our full emission data. Another aspect of this kind of correlation-driven flat band is that as we change temperature, what we observe is that the spectral weight or the coherence of these extremely flat bands also disappears slowly as you crank up temperature. So you can see here this band is gone when we raise the temperature, and also the hybridization with other stuff, the dispersive states here, also it's turned off as you go. So in summary, for these correlation-driven flat bands, there's as the more flat the bands are, the smaller the quantum particle coherence or the spectral weight, And then, because they are induced by correlation, then the location of these flat bands are, very much close to the Fermi level. I think this is what a lot of us already know. So in contrast, let me just to show you some example on the other side of this, which is the case where we are maybe in the recent years very popular in the field. So the poster child of this is this Kagome metal. This has been discussed a lot in the workshop. So in the metallic regime, because of the destructive interference of the electronic wave functions, these so-called compact localized states are, they're forbidden from hopping to the next one over. So in momentum space, they become completely delocalized into flat bands. And this is the nearest neighbor type binding calculation. And in real bulk materials, the best case represented is by this Cobalt-tin from Ricardo's group's work. And you can see that here, the DFT actually works very well in describing where and how the flat bands should look like. And you can see that these types of flat bands have the full coherent spectral weight, just like all the other dispersive states. But obviously in this situation, the location of the flat band in energy is not special in any case, right? So this depends on the filling. So these are aspects which are distinct from the correlation-driven flat bands.
Yeah.
We've also worked on various types of these Kagome materials, and I'm actually not going to talk about these, but my postdoc Zhengren here is a poster talking about our MBE grown iron tin film measured with photo emission, where we can first time look into the nature of the magnetic order in these magnetic Kagome systems. So you can still have if you.
Sorry, can maybe just so I understand your approach. So I understand that if you have the flat band coming from no interaction electrons, then any small interaction will make it correlated. But in the other case you're talking about, you kind of already used the interaction to get a flat band. So what then? I don't expect to have another instability of that flat band towards something, right?
Right.
So is this a fundamental difference between these two, or
I think that's what I'm basically driving at. Yeah.
Oh, okay.
Yeah,
So
yeah.
that other flat band is not to get to something,
Yeah,
but they're
yeah.
already okay.
Yeah, that's right. Yeah.
Since you mentioned that, can I also ask
Oh,
a question? What's the smallest Z that you can measure in photo emission? You said that there is small quasi-particle rescue Z. What's the smallest value
that's
you can
so
reasonably measure?
I can't put a number on this, but this is
That's
we can measure a trend, I guess. So in the case of this so we can infer that from the spectral weight or also from the effective mass. I don't know. I would say I can't put a number on it, but yeah. Anyway, we can talk about this later. Yeah. Sorry. Okay. So that's the 2D case, and I also want to throw in this slide looking at the 3D analog of this, and as we know from the quantum spin liquid field, the 3D analog is the particle lattice, and this also in the metallic regime gives you geometrically frustrated flat bands, and so very quickly. So the way we can see that is that I forget somebody mentioned yesterday that there's a way to cut through the particle lattice at the 1-on-1 direction where you can see the Kagome planes, and there are 3 ways to cut this. And so here, if you calculate one amplitude for the 4 sites, in one of these tetrahedra, the one that's not contained in the Kagome plane has identically 0 amplitude. So what this means is effectively we can think about the particle lattice as 2 decoupled Kagome planes. So everything we know about the Kagome lattice is retained, and also the outer plane hopping is also quenched, right? So here the destructive interference is in 3 dimensions. So the result is that if you do the tight bending calculation, you'll end up with 2 copies of flat bands, and then in addition to dispersive states. So the key, the electronic signatures associated with the pyrocore metal is that you get 2 copies of flat bands, and there's also actually a Dirac point everywhere when you have a band crossing at the X point, and these are gapless Dirac points protected by a non-symmetric symmetry associated with the pyrocore lattice. So And we first encountered this physics in this lava phase, CM2. And for more details, you can refer to this paper. And also, George group has recently also a paper discussing the lava phase. So this is talking about flat bands in 3D. So we also identified another paracore lattice, which perhaps has a better preservation of the flat band. So this is the Spinel lattice, copper, vanadium 2, sulfur 4. And in this Spinel structure, the vanadium sublattice is a paracore. And it turns out that in this kind of structure, the electronic states associated with the vanadium T2G states are the ones at the Fermi level, and they have very little hybridization with the other copper and sulfur. So here, the paracore flat band is actually preserved very well in the structure. And so that is kind of nice. But what's surprising is that when we did photoemission for this compound, we can actually do photoemission on these cubic materials. But here in the photoemission, we see that the flat band is actually right at the Fermi level. And you can see that here's the image, and these are the energy distribution curves, very sharp or relatively sharp, at least coherent peaks at the Fermi level. And so here, if you look at the DFT, this flat band actually should appear about half EV above the Fermi level. And so, given what we know, and so our thinking about why this flat band is actually appearing at the Fermi level is because of additional correlation effect associated with T2G states. So here, again, we collaborate with Timel's group, who did a state spin calculation, and they can see that by incorporating Coulomb interactions U, and also on state, they can bring the flat band closer to the Fermi level, which describes or matches with the data better. So in this situation, we actually see the two contributions. One is that you have the geometric frustration associated with the paracore lattice to make the flat band first, and then by additional of the correlation effects from the d orbitals, then these flat bands are brought closer to the Fermi level. So this is, I think, is a very interesting system that we may consider. There are actually other members of the Spinel family. A more famous one is lithium vanadate, which is I guess the only one with d electrons that's on the heavy fermion plot. So, and we suspect that likely very similar situation actually is occurring in that system as well. So that's the connection. Okay, so these are examples of the two ends, and I hope I try to convey that fundamentally, these are different objects, even though they both have flat bands. And what will be interesting is we want to, and there's been recognized, of course, in the field by ways to think about this analogy. So here are some work exploring how we can map one to the other. And this is, I'm sorry, I'm not being all inclusive. I apologize about that. But this is one explanation from Timel's group where they treat the topological flat band and the white band, which it touches, as a single object, and then this forms this what they named the compact molecular orbitals. And with this object, they can do the one-ization, and then use a model which is very similar to the heavy fermion system. And here's another example from Andrei Bernovich's group that does this in a momentum dependent way to tackle this situation, which is about the graphene and other TMD material. So this analogy is recognized, but then the question is, I guess, so as because they're fundamentally very distinct, so how do we think about, what role do they play in quantum materials in terms of in connection to electronic orders and so on and so forth? So the best way to do that is to perhaps find a system where both can be observed. And this is relatively difficult in general, because in order to get this type of flat band, you really need a special lattice. And so how to have these in the same system is in general not easy, but we happen upon a system that does actually let us switch between these two types. And that's the story I'm going to tell you about for the rest of the time. And hopefully maybe get some feedback from the audience as well. So how do you do this? So with this is the scenario. One way how we can approach this is if you consider systems that are not stoichiometric, they have missing sites. You can call this vacancy or site ordering. So here, you can consider the two situations. Suppose you have vacancies in the lattice that appear in an ordered fashion you can imagine there are situations where this could lead to special types of lattices that may fit with this type of topological flat bands. And then you can imagine if you have the same number of atoms, but they're arranged in such a way that the vacancies are random, then you have globally different symmetry. And in this situation, this kind of geometric frustration is actually turned off. So you can imagine situations where in certain materials, there is a vacancy that could order or disorder, and that can give us to one of these situations that maybe perhaps is a way to turn on off this topological flattening. So that's what we discovered accidentally, but this is at least the central idea behind this. And that material is this, 2 dimensions of van der Waals ferromagnet, iron 5, germanium, tellurium 2. And this is known, I guess, also quite popular material in recent years because it's discovered that if you exfoliate this to the thin limit, it retains long range magnetic order. But so this is I guess the end goal, what I'm going to try to tell you for the rest of the talk is that we can actually realize 2 states where we have a vacancy order phase that gives you topological flat bands that behaves very differently than the situation where we have the vacancies that are on random sites. So that's the story I will tell you about for the rest of the time. Okay. And I will do this in 3 steps. The first, I will introduce the bare minimum of what we need to know about iron, germanium, tellurium 5.2, and then show you our best evidence of these flat bands and how we understand the origin of these flat bands. And then lastly, some mumbling of what we think are potential consequences of these flat bands in these materials in relation to their magnetic order. Okay. Iron, germanium, tellurium is a big family of metallic ferromagnets. They all largely look like this. They got van der Waals slabs. The difference is that within each slab, you can think of this as a sandwich. This is the bread, which is tellurium. In the middle, the green stuff is germanium. The difference is the amount of iron in between, right? So I'm only going to focus on the iron 5 version today, not just because it has the highest TC of near room temperature, but also critically, it has a very important tuning knob, which is different from the other 2. That's the vacancy order. Okay, so I'm going to use this one slide to try to tell you the key point of how the vacancy order comes into play. So please bear with me. So this is the TEM image from the Oak Ridge group, Jume's data. So this is a side view cut, and then you can see the van der Waals slabs. In a single unit cell, there's ABC stacking of the van der Waals slabs, and overall structure is central symmetric. So if to show this, I can blow up one of these slabs. If you look at the structure, the inversion center is in between these 2 split the blue dots, right? So there's first the tellurium pair, which is inversion symmetric, and then you got 3 pairs of iron sites. The inner 2 pair are obviously inversion symmetric, and they are always fully occupied as far as we know. For everybody else knows. The last pair, the iron 1 site, if you have exactly iron 5, 1, 2, then for each pair of the iron 1, each up-down pair, you can only occupy one and only one of them, right? So that would give you iron 5, 1, 2. So the key point is that people have found that this crystal structure has 2 stable forms. Whether the iron 1 chooses to occupy the up one or the down one could be completely uncorrelated and across the sample. And in that situation, you can consider the iron 1 site being on average 50% occupied. In that situation, the global inversion symmetry is actually preserved. And we check this with second combiner generation measurements with Neil's group. The lattice could also be stable in another form where the choice of the up one and the down one forms a pattern spatially into this up, down, down pattern, right? So it goes up, down, down, up, down, down. But you can see that the sites that they occupy are actually identical, and the number of atoms within the inner cell are also identical. It's just the way that the vacancies or the sites are ordered is different. That's the only difference between these 2 phases. Okay. Okay, all right, so why am I telling you this? Well, the biggest difference of these 2 is that imagine we take a horizontal slice through the plane that contains this iron one site. And then that will actually precisely give you this view, right? So here on the right hand side, if you walk horizontally, you will see this is these are the occupied one, and the next one is the missing one, so on and so forth. And this gives you this ordered view. And then on the other side, you have the 50% average occupancy of the red one. Now this one turns out to be a very special lattice. Oh, sorry, this has been seen in TEM and XRD, and also resolved by this STM work that actually sees this repetition of these kind of clover shape. So it turns out that after some discussion with our colleagues, and we now think that it seems to us that this clover unit is quite special because it's made of two sublattices, the red one and the yellow one. And so here, the nearest neighbor hopping is always between the two different sites. That makes this a bipartite lattice. And theoretically, one can show that if the number of sublattice A and sublattice B within the unit are different, that difference is the number of guaranteed flat bands you would have. And that's indeed what we would see if you do the tight binding calculation, taking into consideration the nearest neighbor hopping. So here is the flat band, and then if you add Blumberg coupling, then there's some curvature, and then vary curvature, and also this gains the turn number. So this would be the type of flat band which is very similar to the type you would get from a Kagome lattice or a Paracore lattice or any of these geometrically frustrated lattices. And that's the situation where you are quenching the coupling from the geometry of the lattice themselves. So this is what we would expect. And what do we see? So we did photo emission measurements for the two types of crystals. You can see that they're very different. So these round things are the Fermi surface that we measure. This is Kx versus Ky. And then these 5 different things are energy versus momentum cuts through half the Brownian zone. And I hope you can see that on the bottom one, there are these like flat objects that are extending over a large region of the Brownian zone, and they are absent more or less, as far as we can tell from the situation where our samples have this random iron one size occupied.
Ming, quick question.
Yes.
So you mentioned XRD and STM results on both faces, right?
Yeah.
To what extent can you, each phase, can you rule out short range correlated regions of the other phase?
Yeah, very good. Thank you very much for this. So we have not yet gotten a single crystal which is 100%. Every single crystal always has two types of phases, but their volume fraction is different depending on, I'm going to tell you about, I guess maybe on the next slide, how one can actually get from one to the other. But in this process, we can see from XRD, we always see the superlattice peak due to this vacancy order. But the one in the, so basically the way to switch is by quenching versus slow cooling. But in the quench samples, you have a much brighter superlattice peaks. We have also done STM with Eduardo de Silva Neto's group. So basically, they only see ordered regions in their field of view for the quench samples. And this one is largely deformed with small puddles of ordered regions. So we have never gotten 100% volume fraction for one or the other, but we can see dominant, like the volume fraction depends on this treatment method. Yeah.
How small the volume fraction of the secondary phase can you achieve?
This depends on, so we're studying this process now. This depends on the cooling rate. Basically, like you would, I can show you some STM result. I don't have a number off the top of my head, but I can, I can show you that. But from the photo emission, you can see, we always see dominantly one or the other. There's one situation where we see about 50% of one versus the other, basically the sum of the two types of electronic structure combined. Yeah. Okay, so the understanding therefore is that these, at least our best attempt at understanding this is these flat bands are associated with this kind of destruction things, and they're turned off for this case, and therefore this is why we don't see them there. But other than that, the crystal structure are the same, except this arrangement. So let me talk about how we get to this is another subject which is very interesting of its own right. It's very counterintuitive. So the way that we can control the majority of the phase is by, so the crystallization temperature is high, and between that and a critical temperature of about 550 K, there lives a phase which is metastable. And it turns out that if you put your sample in this region and then you quench it in ice water, the sample has a much larger volume of the ordered phase. This is the counterintuitive aspect. But if you slowly cool it, the sample has actually much more disordered phase. And we're studying this process now. We just recently took some single crystal XRD data from chess during the quenching process, and we can see the formation of these during the quenching process. But we're still analyzing this, and I think given what Ray showed yesterday, it's obvious we need to go to APS and do diffuse scattering in this process to understand this process. Yeah.
How cheap is the material? How anisotropic it is?
I think that's the number, but all I can say right now it's venerable sample, but
so it's to measure resistivity, it's very anisotropic.
I can't remember the ratio, but it's fully both. Yeah, yeah. Okay, so which phase actually ends up in affects the magnetic magnetization. So this is magnetization measurements taken on samples that are quenched versus slow cooled. And here, there are a couple differences. Actually, I'll come back to this curve at the end of the talk, but you can see one obvious difference is there's a kink for this situation around 100 K. This is the impurity from the other phase, but I will actually come back to this a lot later. So this does affect the magnetization of the crystal. Okay, so here's the recent data we took. We want to be able to understand, like how these flat bands actually are involved in the magnetic order. So the way we do this, we can do a very fine temperature dependent RPS measurements. Okay. So the way we do this is that we can take a horizontal slice. These are called momentum distribution curves, and then just crank the temperature as we measure, so we can get a very smooth temperature evolution. And from this, you can clearly see phase transitions, and you can already see that for the two phases, they're very distinct. And let me walk you through them one by one. Let me first look at the bottom one. This is the one with the ordered vacancies, and this is the one where we see the flat bands. If we look at this dispersion, here are the three flat bands, we can choose a region in the momentum space where if you do a vertical cut, you can see the peaks that correspond to these flat bands. And as you warm up in temperature, you see these, at least the two closest to the Fermi level, eventually merge together. We've also done spin resolve RPS measurements on this guy, and we can actually see that these two flat bands closest to the Fermi level have the opposite spin polarization. So what this is suggesting to us is that this is almost a textbook like behavior of what one would expect from a ferromagnetic order, where you have a large density state and then they are spin split at the Curie temperature here in TC. They actually pertain the full spectral weight coherence over the whole temperature range. While this is very textbook-like, I just want to state that this is actually very rare. If you look through RPS literature, this kind of behavior of spin splitting at TC is actually quite rare. And the reason is because, let me just put this into the perspective of other systems that are well known. So we know that we can understand ferromagnetic order in 1 or 2 limits, or if you have an itinerant system, you expect the spin splitting to appear exactly at TC. But if you have local moments, the local moments themselves are persisting up to high temperature. It's the coherence which disappears at TC. So actually, if you look at the band splitting, the exchange splitting actually is always persisting across TC. It's just the spin polarization disappears, right? So actually, for most of the material, especially iron-based stuff, it's very rare, or at least I don't think I've known any case which actually follows exactly this situation. So here is the data from the literature taken on iron film, and here. The blue dots is the spin exchange splitting measured from full emission, and these squares are the spin polarization, which exactly dies at TC. But you can see even for iron film, the spin splitting actually persists at much higher temperature. That's evidence of local moments. But in this situation, we actually see the spinning onsetting at TC, which is actually, I think, quite rare as we have seen. Okay, So that's the first half of the two phases. This is the phase where you have this lattice, the vacancy order. It produces these flat bands due to the geometric frustration, which then split across TC. This is our observation, just observation. Okay, so now let me briefly talk about the other phase, the site disorder one. So here, there are two features which are interesting. So these are cuts taken as a function of temperature. And I hope you can see that as you go across some temperature scale, which is the 100K, everything just becomes suddenly very broad. And here, you can read that all from this temperature-dependent measurements. There's a very sharp transition where the system goes from coherent to incoherent at 100K, and that 100K temperature scale corresponds to this kink in the magnetization curve. And now we know, okay, almost done. Now we know that this is actually this behavior is only associated with the site disorder phase. More interestingly, if we look close to the Fermi level, we actually start to see this flat feature. And we can track this feature by looking at the EDC, the hump in the EDC as a function of temperature. We can extract its spectral weight. It slowly decreases to 0. And this behavior, the disappearance of the spectral weight, is very reminiscent of what we know from the orbital selection stuff I showed you at the very beginning of iron peptides, right? So this kind of band cannot be due to the geometric frustration, but this behavior is very similar to the case of correlation-driven situations. That's the second part. So I really am low in time. I just want to make maybe one comment about what exactly is this thing. So remember, these two crystal structures are largely identical, except where the vacancies actually appear, right? So the total number of iron is actually the same. So if you count up the nearest neighbor, the bonds, they're actually the total number over the sample is the same. But in the two phases, the one with the vacancy ordered case, you have a higher TC here. You can compare the two. And also, all the irons order together at this higher temperature. But for this one is actually understood to be the actual ordering temperature for the iron 1 sites, which are disordered. So they are fluctuating up here, and only at this 100K do the randomly iron 1 sites order. And that we recently confirmed with I need to show one neutron data from Huibo's house measurements. So he did a measurement that utilizes polarized neutron diffraction to actually show that for the region where we look at the superlattice peaks, which is the site ordered only region, there's no additional enhancement between across 100K. But for the other region, which also includes the site disorder phase, you can see this is compatible with understanding the iron 1 sites become ordered only across the 100K. So I think this is something we need to understand. We still don't quite understand why the TC is higher for this one. So this is something that maybe we can get some insights from some of the experts here. But here, just to summarize, we see the situation where in the same chemical or largely the same material, we can actually switch back and forth between the two cases where you have this vacancy order phase, and that drastically affects the electronic structure because of this geometric frustration, which gets turned on and off. And also, it seems to have also some connection or correlation with the magnetic order that appears in this material. So I really ran out of time. Sorry. So this is just to thank. This is my group as this last summer, and the 2D magnet is mostly done by Han Wu, who's going to graduate in a month. Zheng is here, who's mostly working on the Kagome system. Yu Chengguo is a student who's also here, working on uniaxial string on iron peptides. The pyrocore system is studied by Jianwen Huang, who's a postdoc in my group. And we have had a lot of collaboration with Qimao Xi's group, Hong Dai's group on the samples, and also Xianghan Chu's group had provided up to 2D magnets, and then calculation from Pinghan Yan's group, and then neutron with Huibo's group. So thank you all very much.
One question.
Sorry.
Thank you. Ming, so when you think of this flat band, you said it's coming from correlations. Could it, I don't know, did you think of maybe it could be coming from just thinking you have a lot of impurities that are forming, it could be just like an impurity band?
Yeah,
it's becoming sharper as you go low in temperature that has nothing to do with correlation. Could that be? Or
that's a good question. So we do see it hybridized with the dispersive states, which would suggest, as far as we can tell. So it does seem to, you can only see it where this, right? You can see it, you can only see it really where this dispersive states are. So if it's in purity state, I would naively expect it to not interact with anything intrinsic. I don't know, maybe
Yeah,
Yeah.
I was just curious.
that's like, yeah.
Questions?
Oh.
That's one from.
Yeah, so a very nice talk. So, what are the other iron sites doing with the magnetism?
They order at the near 300K. So the iron sites, right, for this one, they order here. For the site order one, they order here. So they're all
They
magnetic.
contribute to the bands or dispersive bands?
So we've tried very hard to match with DFT and nothing matches. So we're hoping we can, so near the Fermi level, it's all mixed basically. So we haven't really been able to pick out which part is from which iron site. Yeah, unfortunately.
Okay, let's thank Ming. Yeah. Blumberg, and I think we're back to yes. And possibly, and it's going to be Raman scattering.
Do I need microphone now? No, I don't. Okay. Okay, so apparently this is the last talk. So I want to thank all the organizers for bringing us all together. It was wonderful, wonderful 3 days. Thank you for inviting me. And I'll try not to mess up. I'll try to do my best. Now, this is not what I'm going to tell you is, well, I was asking what topic is there appropriate for this workshop. I was suggested to talk about Kagome. And in many sense, this was kind of a spontaneous research. It wasn't that I wrote a proposal, I thought through what I'm going to do, and we did the measurements and confirmed everything that we planned. It was quite opposite. I had a good postdoc, Xianghan, who is currently in Beijing. And it just happened that in this time, this material popped up. And almost instantly, as the material popped up, all kinds of miracles were reported. Broken time reversal symmetry by STM, by muons. A lot of that stuff was never confirmed. At least I don't know that this measurement was ever confirmed, etc. But when topics pops up, people want to do something quickly. Steve Wilson gave us beautiful samples of this 135 phase, and having a good system, we were able to obtain a lot of data. And then the question was, so what? What do you do with this data? And at that point, I remember that instead of going to AI, I remember talking about symmetries to Raman, and Raman provided human intelligence to both of these projects. And I learned a lot. It turned out that there's a lot of group theory that I didn't know. And I was very happy to learn all this in these two projects. So the first project was on this, well, it's different days, but V3SB5. And the second project, the story of this was that when we already had this data and almost submitted this paper, Penjan said that, Penjan Dai, well, the Rice collaboration said that, well, we discovered a new magnetic Kagome system. And well, I briefly conversed with Turan, should we even touch it? Because we had enough trouble here. And well, we discussed that. Well, it's as simple as one can imagine. It's a binary. Gave us a lot of trouble. But okay, I'll tell you what we learned. Okay, so please interact me. Please ask questions. I'll give you the conclusions right away, and maybe I will not get verified and stuff. So we did polarization result Raman study. Means that as an output of this measurement, which is in this case all phononic measurement, we are not looking at electronic response, we're really looking only on phonons. And we are finding the symmetry of the mode, and there are, well, obvious allowed modes, and then the transition due to broken tangles and symmetry, or excuse me, due to broken symmetry, not tangles. Yeah, the new modes appear, and those are amplitude modes in some cases, etc. So we were dealing with the entire zoo, and the unit cell is pretty large, of this mode, and try to make sense of them. And we learned from this system that the order parameter is not at all trivial. It's not one symmetry broken, but there is at least 3 broken, and there is a combination in the Landau expansion, and the trilinear term allows to have coexistence of different order parameters. And all this kind of popped up from this study. And from this study, the story was even more interesting, because what we learned is that when we go, let me go back. When we go from paramagnetic phase, which is indeed trivial phase, the first phase transition is in A-type antiferromagnet. And at this transition, what we discovered at the first time, that it's a Kagome system. It has C6 symmetry. C3 is broken. It breaks with entrance of after antiferromagnetic phase. Right. So then there is a quite complicated charge density wave, 3Q charge density wave phase that comes in. It maintains also the antiferromagnetic phase. And then there is another transition, which is so-called spin-cantic transition. And the biggest surprise here was that in this phase, which is a low temperature phase, the broken symmetry recovers. So at high temperature, you break the symmetry, and then, well, violating laws of thermodynamics, you would think initially, it recovers. And you clearly can see from the Raman data that this is the CDW phase. You see new modes appearing here, and I can tell you a lot about those things. But this is in the low temperature phase, the situation recovers back to the one single allowed mode, and well, we have some explanation why. Now, there's a lot of discussions why Kagome is interesting and why we get these flat bands and all those things that, well, in practice are 2 electron volts away and probably not important at all. But nevertheless, people believe that in this 135, the superconductivity is unconventional, and et cetera, et cetera. So I'm going to skip this slide and tell you about these 2 systems. So there is this, so this system, the cesiums are not interesting decorating ions. And the interesting part is this vanadium Kagome-net, which is in this plane. I'll show you a better picture of it. And the other material, which if I ever get to that part, is this binary material, which looks extremely simple. So this germaniums and those irons, it's a magnetic material. And I will contrast these two stories. So cesium B3, antimony 5, magnetization, resistivity, heat capacity. This is the CDW transition. And then below 2.5 degrees, there is a superconductivity. The superconductivity emerges from the CDW state. And well, people talk about various miracles here. This slide I already flashed. There's data that wasn't reproduced. There is data which is kind of showing broken time reversal symmetry already in CDW phase, at least the claim the paper. It's otherwise you don't get in glossy magazines, right? But there's more and more evidence that there's some surface effects and other things. Yes.
So I just need to defend some of the people here.
Right.
The SPM has been reproduced by 2 different groups in 3 different kinds of samples. So you may disagree with the interpretation, but the exact data has been reproduced, different groups, different samples.
Field trained, right?
No field training. I'm talking about the STM.
Yeah, but it's field trained this year.
There's no field training. We can talk about more later, but
okay,
it's not true. This is a robust observation.
Good. No, I'm not aware of that, so it's good you pointing out.
But the time reversal, I mean, the curve measurements, for example, were not reproduced.
We can talk. I don't want to hijack the talk.
Yeah.
I just wanted to make that point.
Yeah, that's good. Yeah. Okay, so focus is on the group theory that I learned from this project. And so those are the layers. So this is the Kagome-net of vanadium. There are 2 sites, different sites for antimony. So one is in the same plane. So then there is a kind of graphite-like net above and below. They have quite different distances. The structure is hexagonal. Void group is D6H, as I said, in high temperature phase. And then the question is what happens at the CDW transition. That's the first question. And already here, there's multiple interpretation. There's a lot of data that says that all kinds of symmetries are broken, and Raffaele will confirm that. So, and we didn't find that. We found that the translational symmetry is broken, but none of the axes or planes are broken. So it remains in fully symmetric. But the devil is in the details, which is interesting, because the question is, what is the instability? How the instability is driven, right? And the DFT data suggested, and this comes from this place, right? So suggested that there are various instabilities possible. So there is instability at M point, which will break the symmetry in plane, but will not double the unit cell along C-axis. Then there is another instability L2 from this point, which will double the unit cell along C-axis. And then there is also instability on this line between M and L point. If you take it in the middle, so-called U point, then you will get a unit cell which is four layer units. Now, we went a step further, and in collaboration with the Weizmann group, Bin Xianghan, we tried to calculate the static susceptibility, essentially following the recipe of Igor, who did the same similar thing on niobium diselenide about 25 years ago. Right, and similarly to that result, what we found that, well, there is no really point where we can see sharp divergency of susceptibility. So U point shows the largest one, so there is enhancement of susceptibility in many points, but there is no obvious yes.
Sorry to interrupt. Is it just free formula susceptibility, or you want to consider some interaction mechanisms that would increase susceptibility?
This is done on the band structure.
Band structure is free formulas.
Yeah.
What about, you said, enhancement of susceptibility? Enhancement on the level of free formulas or enhancement due to?
No, this is bare susceptibility. There is no enhancement in this. So this is what you put in before you turn on the interaction.
And interactions are interaction between electrons. It's not just phonons.
No, it's all electron phonon. Okay. I don't think there is a. Well, I'm not aware that it's electron. So yeah, you just want to look for the place where the chi zero is large, and then you can do coupling to phonon, and then you expect instability. But anyway, so that by itself doesn't tell which of those points would be leading. But what turns out that, well, those are all 3Q instabilities. So for M point, the picture is just this. Obviously, you get from Kagome Stahl-David instability, and in some cases you get inverse sum of Stahl-David instability if you at U point. And so this doubles the unit cell, as I already said. This opens the unit cell. If you add them all up, if they are allowed to all coexist, and they are allowed to coexist because they turn out to be in the same representation, so that's where the group theory comes in. Then you get quite complicated charge density wave, which you get in this material. And an interesting part of that was that after Steve Wilson's group did careful refinement of displacement, then it turned out that if I just plot the modulation of every of these three instability order parameters and sum them up, so those are data points. They quite well describe the situation for the vanadium displacement, and same actually works also for cesium displacement. So it's yes.
So since you mentioned Stephen's refinement, he found in the refinement an orthorhombic spacement, and you're saying that you don't see any of these distortions. I'm just curious to know.
Yeah.
Could it be a resolution like you see if there's a splitting of the EG phonons, it's just too small to see, or?
I'll come to that.
Okay.
I'll come to that. Right. So, in this initial paper, we were entirely in agreement with what they found. I mean, all displacements are entirely in agreement with that first refinement. Now, this will give background to Raffaele's question. So now the homework, that's what I was learning from Turan. So when you backfold every of this instability point on the gamma point to enlarge unit cell, you get the new modes, and your ground state has to obey distinct symmetries. And turns out that both these M and L points give the same two possible symmetry of instabilities. It's either full symmetric, you don't break any symmetries, or it's E2G, which would break the symmetries as Raffael's. The U instability is, in addition to that, you also can break inversion. Now, which of those is going to be a ground state is, of course, question of energetics. You don't know. However, doing spectroscopy, so that was kind of one interesting result, is that we found out that these two states are not far apart. So one is the your real ground state, another one is failed order parameter, which you can excite or you can induce by different methods. And indeed, there is a large amount of literature which claims exactly what Raffaele pointed out, that there are broken symmetries. Besides the translational symmetry, there are broken mirrors and broken rotation. Now, by doing this Raman study, I'll skip that. Well, I'll come back to this plot, but let me give you the result. By doing the Raman study, and I'll show you why, we kind of very convincingly showed that we are dealing with this full symmetric representation. So it doesn't, the ground state, the true bulk ground state, doesn't break any symmetries. And I was very happy to see this publication recently from the Washington group, where they did elastoresistivity, polarization resolved elastoresistivity, so they can look for two different channels, and they see anomalies in full symmetric channel and very little of stuff in the C2G channel. And they don't see anything in any other channel because, well, the symmetry doesn't allow. They also see another transition at T star, which we also noticed from the phononic study in the Raman days. I think I should. What is the time?
It's about 10 minutes.
10 minutes.
12.
Yeah, I'm going to skip the standard free energy part, but I want to show some of the Raman data that appears in that. So this is the main mode, which exists in high temperature phase, and then here you see either folded phonons or amplitude mode or all those things. And they are all, because I want to get a little bit time on iron germanium, so I will be quick here. But to emphasize this point is that in order to have broken C3 symmetry, the double degenerate modes have to split. And there is whatsoever no splitting. This is the main mode that exists high temperature. There is no split. Now, however, these other results were obtained either on the surface of samples, so they're cleaved, the STM that you said it was reproduced, or there's a lot of study done by pump probe. So you come in with high energy photon, you excite everything, and then you look after the excitation, and you do see broken symmetries. And my take on that is that the ground state of E2G symmetry is just not very far from your real ground state, and therefore it can be induced by strain, by surface, by all those kind of effects. All right, I think I skipped the many details here, but I'm going to skip here. I wanted to say that we see anomalies, well, we see behaviors of hardening of the modes, which are kind of a signature of amplitude modes, and there's more than one. And we see also other instability that comes in at lower temperature. And again, this trilinear term in the free energy allows to have another phase transition. And well, the details are given in the paper, so I'm not going to say more here. I drop here as a conclusion that so the main claim was that the ground state doesn't break any mirrors, any rotations. It's only translational symmetry that is broken, but there is nearby another state, and it can be thermally excited. It can be excited by help of surface, etc. So it's a complicated thing, and that doesn't include anything about superconducting state, which the reports of which also include statements of broken time reversal, etc. Now, it's difficult to see really any reason for broken time reversal also from the perspective of, let me get to this plot, because when we really look for the instability, we do the symmetry analysis of all modes, and we see nothing in this so-called antisymmetric and the XY exchange, A2G representation. And A2G representation is the only one that is compatible with time reversal broken. So we don't have anything to grapple. So I'm quite skeptical that all the claims of broken time reversal symmetry are relevant. Okay, so let me switch gears. 5 minutes, yeah? Okay. This is the paper from Rice, claiming this discovery of density wave in Kagome lattice. So paramagnetic state, A-type antiferromagnet bilayer. Then it's CDW, and then it's more complicated stuff. So the more complicated stuff is here. It's a coexistence of antiferromagnetism with CDW. Now, surprisingly, what we found that already at this Neal temperature, this transition, C3 is broken. So this phase has only C2 symmetry. And let me quickly there. So calculation of Turan's group said that the lowest point here, instability point, is A6 minus, which means that what we actually have is, this is consistent with moving in opposite direction in neighboring plane. And by doing that, well, first of all, you break the C3, but also you may modulate the interaction, magnetic interaction, or super exchange passes, and maybe you get some kind of spin Pierce-like contribution, except that atoms and ions are not moving in this direction, but you are decorating super exchange, which is between this layer and this layer versus this layer and this layer. So it's entirely a possibility.
So the ordering wave vectors are the endpoints, like in the previous compound?
No, this ordering vector is A6 minus in this case. So A point doubles the unit cell, and then 6 minus gives you this patch. so that by itself is kind of non-trivial. And then let me get to the punch point, which is that what we see is so the fact that we see this broken CP symmetry is because of we see the splitting of E mode. E mode splits in two modes. I rushed that part, but it's clearly seen in the data. And then the most interesting part of it is that in this paramagnetic point group iron Xianghan, there's only one allowed Raman active mode, which has E2G symmetry. It's double degenerate mode. Right. It splits when you go from high temperature phase, paramagnetic phase in antiferromagnetic phase, and then it recovers. Essentially, the low temperature phase is essentially same as the high temperature phase. So here it's already broadened because of interaction. Here is the low temperature phase. It's central. So the claim here is, again, I repeat that, I skip all the free energy analysis, but the claim is that so this quantum transition is a magnetic transition. And so if you recover the symmetry, you need to deal with the entropy. Because the symmetry gets broken each time, the symmetry should get lower. And if it gets recovered, where does it entropy come? To recover, right? And the story that we put forward in that paper was that the displacements, atomic displacements, are very weak in this system. It's not the usual CDW where the phonons are kings, and I mean, there's a large, all displacements are relatively small. And it must be that then the magnetic transition comes from this A-type antiferromagnet to spin counting orientation. So the entropy gets borrowed from that magnetism. So the total entropy is okay. So we are not breaking third laws of thermodynamics, but that would at least, well, we don't have any real calculation of that, but well, that hypothesis was put forward in that paper. Yeah, but the fact that it recovers is a solid statement because it's spectroscopic. All right, so I'll leave you with these conclusions. And again, thank you for your attention. Thank you for staying to the very end of the workshop.
So I actually don't have a question. I'm gonna ask, I have two requests. Okay. I about the Kagome, the first Kagome. I generally agree with what you're saying. I think some effects are a little more subtle. So the first one is that Stephen Wilson has done a follow-up X-ray refinement. Yeah, and he does claim that the refinement is best fit by the neutron group. I think since he gives all the lattice distortions and parameters, it would be nice just to compare with the fitting that you showed to see how different they are. Is it like a minor difference or not? Well, for the Raman. Yeah, the answer to that is, before you go to the next question, the answer to that is that isn't the resolution that we have, we do not see splitting of EMF, and that's a very solid state. No, and well, this elastoresistivity measurement is also very consistent with that. I agree. Those are all bulk probes. But X-ray, I mean. X-ray is bulk probe, but refinement is very tricky business. Fair. The second point is that Turan and I, when we propose to explain all these claims of time reverse symmetry breaking is that there is time reverse symmetry breaking, but it's not, you know, a magnetic moment showing up, it's piezomagnetism showing up. And that we show, or we claim that it explains all this, the STM, the controversy with the curve. But you could actually prove us wrong by, if you do your Raman. So if we are correct, if you do Raman under a magnetic field, which my understanding is that that's doable, you would see, if we're correct, you'd see a splitting of your EG mode. And if you flip the magnetic field, well, we're not going to see it, but yeah.
Well, 1 second. So the reasoning that you bring forward is due to interaction of these circular motions of electrons to
co-orbital magnetism, but sure,
yeah,
you can think like that.
to the lines.
Right.
Right. So this the signal from this material is actually quite weak, and we haven't done any electronic scan, just very difficult. So on the level of phonons,
yes,
I do not believe that we will see any review in the field applied.
Well,
but again, if you apply field, you break time reverse on people.
But you wouldn't have a splitting of the ED to G mode by applying. We can talk more, but it's a very well.
Yeah, I have a more simple question about the second part. I have also a question on the first part, but let me skip it. On the second part, just a question about wording. You said restoration of symmetry.
Yeah.
Does it mean that in reality you have some other magnetic order, canted order, which just replaces charge density wave and original antiferromagnetic? But the state is still ordered. It's just differently ordered.
It's ordered differently. There is a second magnetic phase transition, which goes from this bilayer antiferromagnetism to the Conti. It actually has also periodicity.
And you are saying with the second phase, there is no accompanied CDW.
Yeah, it looks like it kills the CDW, but CDW by
Could it be that CW moves somewhere else in Q space? That's
Yeah, that's another possibility. Yeah.
Yeah, this is another possibility. Sure. Well, I mean, we don't see a point anyway, right? We see only resulted update faults in gamma. We don't see that, but if it's yeah, I mean, if it's not a condensed space, I mean, it's a silent cube.
Sorry, CW is by neutron is still persisting even in the lowest temperature phase.
Right, their brackets claim to persist in that, but again, it's amazingly we don't see any folded modes and they go away. So there are troubles with the fully interpreting all these results because
Oh, it's good. We have still troubles to think about in the future. I think we should now thank Girsh. Yeah.
Hey, thanks everyone for participating, and those who traveled, we wish you safe travels back. And those of you who have posters, still please collect them on the way out.
I just wanted to say there's three of us.
I don't have a lot of it, but I made a first.
Thanks, Zach.